Okay, I plan to go through this pretty quickly, so you might want to pause the video here and there and take some notes. Here's the original function, a rational function. We're supposed to find intervals of increase, decrease, concavity, and some other stuff, and then sketch a graph. Okay, so first derivative. I'm not going to go through the steps, so I'll just you take a look at it, but we apply the quotient rule to end up with this, or we want to factor the numerator x times the quantity x minus 6. The second derivative, again, the quotient rule, after a bunch of simplification, simplifies to this. And we'll come back and use those two derivatives later on. So the first thing you want to do is figure out the x-intercepts, which happens when the numerator is 0, or when this expression equals 0. That only happens when the numerator equals 0, so that's 0, 0. Similarly, for the y-intercept, when x is 0, we get 0 over -3, which is 0. So the x and y-intercepts are both at the origin. And that's the only place where the graph crosses the x or the y-axis, nowhere else. The vertical asymptote is at x equals 3 because that's when the denominator equals 0. There is no horizontal asymptote because the degree of the numerator is greater than the degree of the denominator. Since it's 1 greater, we can say that there's a linear slant asymptote, sometimes called an oblique asymptote. Here's how you figure that out. If you divide x minus 3 into x squared, the numerator, this is what you get by long polynomial division. And that part right there is this equation of the slant asymptote. And so you can see as x approaches positive infinity, will always be, because of this term, a little bit above the slant asymptote. The function value will be above it. As x approaches negative infinity, this term is negative, so we'll be below the slant asymptote. Okay, so you also want to decide what's happening as you approach the vertical asymptote from either side. So as x approaches 3 from the left of 3, you can say, well, what happens to this thing when I put numbers in here like 2.99? Well, the numerator will be positive, and the denominator will be a very small negative number, like -0.0001. So it's going to be approaching negative infinity. And similarly, from the right side, if we put numbers like 3.0001 in for x, we pause, we approach right, approach positive infinity. And finally, we'll apply first derivative test. We could apply the second derivative test also, but the critical numbers are 0 and 6. And of course, the first derivative is undefined at 3 because the original function is undefined there. So I like to draw a little dashed line there to represent the vertical asymptote, x equals 3. And so to the left of 0, the left of that critical number, the first derivative is positive. You can put like a number -1 in for x in this factored form. The denominator will always be positive. So we get negative times negative is positive. So increasing, and there's that, to the left of 0, there's the part that's increasing. To the right of 0, decreasing, but we'll never cross that vertical asymptote. And to the right of 3, but to the left of 6, negative, decreasing, coming down this way, and to the right, increasing. And by the way, when x is 0, y is 0. But when x is 6, y is 12. So this is the point 612. That's a relative minimum. And the test for concavity to the left of 3, this thing is always negative. So always concave downward, and that's what this branch looks like right here. And to the right of 3, the second derivative is always positive. So concave upward, and that's what this looks like. So there's what the graph looks like on Desmos. There's your relative maximum. There's your relative minimum. Slant asymptote, vertical asymptote. Bingo. Okay, if you have any questions, post a comment.